Hello class and welcome. Today we're going to be talking about a mystery, and this mystery is what changes momentum? What causes momentum to change? Today for right now we're going to be ignoring the whole vector thing and we're just going to be focusing on the basic idea of momentum. Momentum as mass multiplied by velocity. Well, if we're going to change an object's momentum, we have to either change the mass or the velocity or both. But you know what? It's very uncommon for mass to change. So changing momentum means changing velocity. All right, well think back a couple units and you'll remember that velocity is changing. Well, that's acceleration. And what causes acceleration? Forces cause acceleration. So it should make sense if I tell you that momentum won't change unless there's a force acting on an object. So forces cause changing of momentum. Look at this bowling ball. It's got a massive m and a velocity v. It's going this nice diagonal direction. It's going to keep going forever due to Newton's first law until it feels some sort of outside force. So its momentum won't change until it feels a force. Okay, so if you want to create a big change of momentum in something, you're going to want a really big force. That just makes sense. But you know what? You know what else counts? Time. So let's say you have a car and your car is stalled and you have to get it up to speed because it needs to go a certain speed before the engine will catch. Oh Lord, okay, hold on. That's kind of a car. Okay. So you want to change the momentum of this car, right? Well, if you were to get behind this car and give it a push for 2 seconds, you're going to change the momentum of the car, right? But you're not going to be changing by very much. If you want to really change the momentum, you have to give it the same push for an extended amount of time. So 2 seconds probably wouldn't cut it. Maybe 60 seconds, okay? So it's not only the amount of force, it's how much time the force takes to act, okay? So both time and force are going to count here. So in fact, we have a new concept, a new physical quantity, which is going to be called impulse. So if I'm pushing this car for a certain amount of time, what we could say is that I'm delivering an impulse to this car. Well, what is impulse? Impulse is defined by force multiplied by that time interval. It's just the product of these two. All right? Symbolically, we would say that impulse is equal to force times delta t. What are the units of impulse? Again, there's no named unit for it as far as I know. It's just Ooh, that's not supposed to happen. Excuse me. Okay, where was I? It's just Newton seconds. So this is the unit of impulse. Okay, so as it turns out, there's a very simple relationship between force, time interval, and the change of momentum. In fact, we can say that force multiplied by your time interval is equal to your change of momentum. Verbally, we would say that the impulse given to an object is equal to its change of momentum. All right. So let's go ahead and actually make a derivation to prove this. We can actually prove this using Newton's second law, okay? And the definition of acceleration. So that's all we're going to do right now. Okay. Well, what is acceleration really? Acceleration is defined as the change of velocity of something divided by the change of time. Let's actually multiply both sides of this by mass and see what we get. Mass times acceleration is equal to mass times the change of velocity over the change of time. Okay. Well, you know what? Newton's second law is going to tell me something. Newton's second law tells me that the mass times the acceleration is equal to the force. So now I have the force on an object is equal to m change of velocity over the time interval. You know what? This is actually looking pretty familiar. Let's try multiplying both sides by the change of time. And I get force times the change of time is equal to mass times the change of velocity. This is very, very close to being what we want, which is going to be the change of momentum, the change of mv. And you know what? We're going to make an assumption here. We're going to assume that mass is constant. So now, the change of mv is just equal to m times the change of v. And we've derived what's known as the impulse momentum theorem. This is your impulse. And of course, this is your change of momentum. Now, we've done all of this without using vectors, but as it turns out, the vector form of this is going to look almost identical. Well, change of time and mass are both scalars, so all I have to do to create a vector form of this equation is remember the fact that my force and my velocity are both vectors. Make sense? Okay, so let's talk a little bit about how this would work if you're trying to, for example, increase your momentum. Okay, so let's say you're playing golf, right? And let's say you're trying to increase the momentum of this golf ball. You want to increase momentum so it'll actually go somewhere. So here's your club. Okay, instinctively, what are you going to do? You're going to hit the golf ball as hard as you can with as much force as you can, right? But you're not just going to do that. You're also going to follow through. That means you're going to follow through your swing, so you're going to make sure the golf club as it swings is in contact with the golf ball for a long period of time. Because the more time it's in contact, okay, the longer this impact takes, the more impulse is delivered to the golf ball, and the greater its change of momentum is going to be. All right? And you know what? In real life, we can't really say that there's one single value for the force of this golf club on the golf ball. In fact, I'm pretty sure that your force is going to change over time. Now, this all happens very quickly, but we can still make a graph, a conceptual graph, of forces versus time. All right? So this is going to be the force of the club on the golf ball, and this is going to be time. Well, at first, the golf club is barely touching the golf ball. So your force is going to be very small. And then what's going to happen is the golf club is actually going to be compressing the golf ball. If you've seen this on a high-speed film, it's really incredible to watch. It actually compresses the golf ball. And as it compresses, that force on the golf ball is just going to increase. And then what's going to happen is you're going to have a peak force. And then it's going to go down. Why? Because by this time, the golf ball has started to speed up. So it started to speed up. It started to stretch back to its normal shape. And the force is going to go down. And eventually, the golf club and the golf ball are no longer in contact, and the force just goes to zero again. Well, look at this. We have all sorts of different values of force. So if we're talking about the impulse on the golf ball, how do we do this? Well, it's actually not too bad. All we have to realize is that we can average out all these instantaneous forces on the golf ball and have a new concept, which we're going to call the average force. So we can represent this real-life force curve with a single constant average force that acts for the amount of time that the golf club is in contact with the golf ball. All right? Now, if this is increasing our momentum, let's now talk about decreasing your momentum. All right, let's go back to a car. Let's say your car is already moving. I cannot draw a car from the side to save my life. Okay, let's say your car is already moving pretty quickly, right? It's got high momentum. And your car is now settling out of control and you need to stop it immediately. You see two paths in front of you, all right? One path has a nice haystack, right? And one path has a nice concrete barrier for you, just waiting there for you, just like this. All right, which path do you choose if you want to stop your car? Without even thinking about it, you know you want to go to the left here. You want to hit this stack of hay, okay? It's going to stop you, but it's going to be a gentler way to stop you than this concrete block. Let's talk about exactly why that might be. Well, in each situation, your change of momentum is going to be the same. It's going to be whatever your initial momentum was, but the opposite of that. So the momentum you need to change and get rid of is the mass of your car times the velocity, right? This is a set amount. You need to get rid of this momentum. What you can change, so as each of these is going to stop you, it's going to deliver the same impulse. So the impulse will be the same. Now, I didn't say that they're going to give you the same force on your car. I didn't say that's going to take the same amount of time for this impact to happen. What I said is the impulse is going to be the same. All right? Remember, the impulse is equal to the force of the object acting on your car multiplied by the time interval it takes to act. So now maybe we can think about this a little bit better. Okay? So why do you want to hit the hay? Because look, hitting the hay is going to extend, just right here. The hay is going to extend your impact time. All right, it's going to make the impact time last longer. Your car first touches the hay. It's going to start plowing through the hay. It has to go to the middle of the hay stack, has to come out the end. All right, it has to roll over any hay lumps out through the end. You're going to have an extended sort of impact between your car and the hay. All right, when you extend your impact time, what are you doing? Well, okay, so your impulse is still going to be the same. But if you have and this is very scientific, if you have a large time interval, you're going to have a small force, okay? So you've decreased your force. You've extended your impact time, and you've decreased the impact force, which is good. I think we should agree that's good. Now, what if you were to hit the concrete barrier? Well, it's going to be a much shorter sort of impact. It's not going to last as long. Your car is going to hit that concrete barrier. It's going to stop right away. So if you decrease your impact time, okay, remember it's the same impulse, and this is very scientific again. If you make your impact time very tiny, you're going to have a very large force to get the same result. All right? So if you extend your impact time, you reduce the force, and vice versa. this is actually a very, very common theme when it comes to impulse. Okay? So, for example, excuse me. Let's say you're trying to evaluate the safety rating of a car, and you're looking at this one car, and it's very futuristic. All the interior panels are made of stainless steel. Okay, this is supposed to be a car interior. Okay, so here's the steering wheel. Here's your nice stainless steel dashboard, your stainless steel glove box, and even the even the steering wheel itself is made of stainless steel. It looks really great, but is it safe? Compare it to another sort of another sort of car interior where everything's made of very soft leather. All right? Again, this is supposed to be a car interior. So everything's made of like either soft plastic or soft leather. It kind of makes sense that this would be safer for your face and your body to hit and impact in the case of a crash, right? So because your body is impacting something soft, it's going to take slightly longer, more time to come to a stop. So your dashboard during a car crash, its job is to deliver an impulse to your body, okay? So it's going to deliver the same impulse if your body has the same initial momentum, right? So what this means is that if you have something hard to hit, it's going to reduce the time and increase the force. We know automatically that's more dangerous. At higher forces, your bones are more likely to break, you're more likely to get bruises, etc., etc. Now, let's say you have a slightly more modern car and we have something called airbags, right? What does an airbag do, essentially? Well, hopefully you'll never have to use one. But in a car crash, what's happening is, the rest of the car is stopping and your body still has a lot of momentum. So we need to stop that as smoothly as possible. So an airbag provides a very large, soft surface for your body to impact in. So it's going to extend the time of the impact between the car and your body. It's still delivering the same impulse, okay? Remember, you're starting off with the same mass and the same velocity in either case, airbag or no airbag, but with the airbag, it makes the time longer. All right? Let's do something even more common. Hopefully you never experienced an airbag. What if I were to throw you a raw egg? How would you catch it? If this egg is coming at you, would you hold your hands out stiffly? Like this? Or would you move your hand downward to kind of give in to the catch? Which is going to have a higher probability of breaking the egg? Well, naturally you would say that you're going to catch the egg as gently as possible, which means really the egg is hitting your hand and your hand is moving down with it, so you are you're extending the impact time. Okay, the egg's got a certain momentum. The egg needs to stop, so the impulse is going to be the same. The impulse from your hand is going to be the same either way. But if you hold your hand out stiff, you're going to break that egg. So there's a relationship between time and force. Let's think of even another example. Let's say you were to jump down from a wall. All right, let's say the wall is 10 feet high. All right. Here's you're jumping down from a wall. There are two ways you can land, basically. Let's say you land the first way, and you lock your knees as you hit the ground. Okay, is this going to be good for you? No. If you lock your knees, the impact time is going to be as brief as possible. and your force is going to be increased. So you probably only do that once. The next time you jump from the wall, what are you going to do? You're going to bend your knees. You're going to kind of absorb the impact with your knees, okay? So that's the everyday way of saying it. The scientific way of saying it is you're going to be lengthening the time of your impact and decreasing the force. So let's actually make some numerical comparisons here. Let's say, for example, let's say that by doing this, you increase the impact time, okay, between the ground and your body. You increase it by a factor of, 8. So it takes 8 times more time. How is that going to change the force on your body, okay? Well, look. Impulse is equal to force times time, or the time interval, excuse me. If this is the same, and if the change of time is 8 times larger, it just totally makes sense that the force is going to be 8 times smaller. And remember, when it boils down to it, force is what's going to be doing damage, okay? It's the force between the bones in your knees, or between the bones in your legs, that's going to break something, or herniated disc or something, okay? So you're reducing the force by increasing the time. And you know what? This is even true for more subtle situations. Here, let me get a new template. All right, so let's say you get a brand new iPhone and you drop it. You have 2 choices on where you can drop it. They're not good choices, but you have 2 choices. All right, there's your iPhone. All right, so one choice is going to be a hardwood floor, and the other choice is going to be concrete. If you're dropping the phone from the exact same height onto these surfaces, it's going to have the same impact speed, so it's going to have the same momentum at impact, so you're going to need the same impulse to stop it, and it's going to stop. You don't really have a choice about that. But you know what? Even though you think both of these are super hard surfaces, hopefully your instinct would be to drop it on the wood floor instead of the concrete. And you know why? Because there's a subtle difference in the amount of time it takes for the wood to stop the phone as opposed to the concrete. Because at the molecular level, all materials have some sort of basic amount of springiness. So this wood, when the phone hits it, it's going to deform just a little bit, okay? It's going to deform and increase the time it takes for the phone to stop. The concrete's going to do that too, but it's going to be very, very, very minimal, okay? I don't know off the top of my head, this would be actually a good experiment to do. If I could borrow your iPhones next time in class, maybe this is, even if this was only, 3 times longer, we can see it would be 3 times less force. So even a small change can make the difference between cracking your screen and not. All right, and one last thing before we're done today, safety nets. If you ever go to a circus, you might see a trapeze artist, like so. And if it's a good circus and not like a bad circus, it's going to have something called a safety net, of course. You guys know the deal. What's the purpose of a safety net? Well, if you were to ask someone on the street why a safety net is better to land in, they might say it's going to give more give, it has more give. But in physics, we would say it has more impact time. So when you land in this net, it's going to stretch and give and take more time for you to land. Okay? In fact, the same concept can be applied to lots and lots of different things. So, you know, if you have a diving board and you're jumping off the diving board, when you hit the bottom, you're going to have the same impulse that you're going to need to stop you. If you have the choice, don't land on the side of the pool where the concrete is, land in the water. Because when you land in the water, you're going to have a much, much greater time of impact. Even though the impulse is the same, the force is going to be much less. Okay? I think that's it. I want to do something more conceptual today. You guys know that in terms of vectors, you know, your impulse, excuse me, you know, we've talked about how to find the change of momentum. And we know the impulse is equal to your change of momentum, right? So we know how to do this already. And we'll get some more practice with the actual vector stuff in class, but I just wanted to make sure we touched on the conceptual stuff. Okay? All right, thank you. Have a good day.